Hey there, science fans. Bill Nye here, ready to explore the fascinating world of data, structures, and algorithms. Just like a good experiment, a well-structured program needs the right ingredients and instructions to work efficiently. That's where data structures and algorithms come in. In the realm of computer science, data structures are like containers that hold and organize data. Imagine them as different types of boxes for your stuff. You wouldn't store your socks in the fridge, right? Similarly, different data structures are suited for different types of data and operations. Algorithms, on the other hand, are sets of instructions that tell the computer what to do with that data. Think of them as recipes. Just like you follow steps to bake a cake, algorithms provide a step-by-step process for solving problems using data. Together, data structures and algorithms form the backbone of efficient and optimized software. By understanding these fundamental concepts, you can write programs that run faster, consume less memory, and handle larger data sets with ease. Ready to dive in? Let's go. Before we embark on our journey, let's get familiar with some key terms. Data structure, as we've discussed, refers to the way data is organized and stored in a computer's memory. It's all about arranging data in a way that makes it easy to access and manipulate. An algorithm is a set of well-defined instructions for performing a specific task. It's like a recipe that guides the computer to solve a problem or accomplish a goal. From sorting a list of numbers to finding the shortest route on a map, algorithms are the brains behind the operation. Now let's talk about abstract data types, or ADTs. Think of ADTs as blueprints for data structures. They define the operations that can be performed on a data structure without specifying how those operations are implemented. It's like having a general idea of what a car should do, drive, brake, turn, without worrying about the specifics of the engine or transmission. Let's start with a fundamental data structure, the array. An array is a collection of elements of the same data type stored in contiguous memory locations. Imagine it as a row of mailboxes, each with a unique address and holding the same type of mail. To declare an array, you need to specify the data type, the name of the array, and the size or number of elements. For example, declares an array named ages that can store 5 integer values. Accessing elements in an array is a breeze. Each element has an index, starting from 0 for the first element, so would refer to the first element in the ages array. Arrays are incredibly versatile. You can sort the elements, search for specific values, and even pass arrays to functions for further processing. They are the workhorses of data storage and manipulation in countless applications. In the world of programming, text is king. And that's where strings come in. A string is essentially an array of characters terminated by a special character called the null character. Think of it as a chain of letters, numbers, and symbols that form words, sentences, and paragraphs. Strings are incredibly powerful. You can concatenate them or join them together, extract substrings, search for specific characters or patterns, and even convert them to uppercase or lowercase. From storing user input to displaying messages on the screen, strings are everywhere. Many programming languages provide built-in functions and libraries for working with strings, making it easy to manipulate and process textual data. So whether you're building a text editor, analyzing social media posts, or creating a website, strings are your go-to tool. Section 5. Structures and unions, organizing diverse data. Arrays and strings are great for storing collections of similar data types, but what if you need to store different types of data together, like a student's name, age, and grade point average? That's where structures and unions come in. A structure is a user-defined data type that groups together variables of different data types under a single name. It's like creating your own custom data type tailored to your specific needs. For example, you could create a student structure with variables for name, age, and GPA. Unions, on the other hand, are similar to structures, but they share the same memory location for all their members. means that only one member of a union can hold a value at any given time. Unions are useful when you need to conserve memory or represent data that can have multiple interpretations. Section 6. Linked lists, dynamic data management. Arrays are great for storing a fixed number of elements. But what if you don't know the size of your data in advance? Or what if you need to insert or delete elements frequently? That's where linked lists come to the rescue. A linked list is a dynamic data structure that consists of a sequence of nodes where each node contains data and a pointer to the next node in the sequence. Imagine it as a chain of objects, each linked to the next. Linked lists offer several advantages over arrays. They can grow or shrink dynamically as needed, and inserting or deleting elements is as simple as adjusting a few pointers. However, accessing elements in a linked list is not as straightforward as in an array, as you need to traverse the list from the beginning. There are different types of linked lists, such as singly linked lists, doubly linked lists, and circular linked lists, each with its own strengths and weaknesses. Choosing the right type depends on the specific requirements of your application. Section 7. Stacks and queues, abstract data types in action. Stacks and queues are abstract data types that define specific ways of organizing and accessing data. They are like specialized containers with rules about how elements can be added and removed. A stack follows the last-in, first-out principle. Imagine a stack of plates. You can only add a plate to the top and remove a plate from the top. Stacks are used in a wide range of applications such as function call management, expression evaluation, and backtracking algorithms. A queue, on the other hand, follows the first-in, first-out principle. Think of a queue of people waiting in line. The first person in line is the first person to be served. Queues are used in scenarios like job scheduling, buffering data streams, and breadth-first search algorithms. Section 8. Trees. Hierarchical data organization. Trees are hierarchical data structures that organize data in a tree-like structure with a root node at the top and branches connecting nodes at different levels. Each node in a tree can have 0 or more child nodes. Trees are used extensively in computer science to represent hierarchical relationships such as file systems, organization charts, and abstract syntax trees. They also play a crucial role in efficient searching, sorting, and data retrieval algorithms. One of the most common types of trees is the binary tree, where each node has at most 2 child nodes, typically referred to as the left child and the right child. Binary trees have various applications, including binary search trees, expression trees, and Huffman coding. Section 9. Advanced tree structures, optimizing for performance. While binary trees are versatile, certain applications require even more efficient tree structures. That's where advanced tree structures like AVL trees, red-black trees, and B trees come in. AVL trees and red-black trees are self-balancing binary search trees that guarantee a certain height balance, ensuring efficient search, insertion, and deletion operations. They are used in applications where maintaining a balanced tree is crucial for performance, such as databases and memory allocation systems. B trees are multi-way search trees that are optimized for disk-based data storage. Unlike binary trees, which have at most 2 child nodes per node, B trees can have multiple child nodes, reducing the number of disk accesses required for retrieval operations. They are commonly used in databases and file systems. Section 10. Applications of data structures and algorithms. Data structures and algorithms are the unsung heroes of countless applications we use every day. From the moment you unlock your smartphone to the time you stream a movie, these fundamental concepts are working behind the scenes to make it all possible. In web search, algorithms like PageRank use graphs, a type of data structure, to rank websites based on their importance and relevance. Social media platforms rely on trees and graphs to represent social connections and deliver personalized content. Databases use B-trees and other indexing structures to efficiently store and retrieve vast amounts of data. Operating systems use queues to manage processes and schedule tasks. The list goes on and on. Section 11. Conclusion: the power and potential of data structures and algorithms. Congratulations, science explorers! You've journeyed through the fascinating world of data structures and algorithms, from the basics of arrays and strings to the complexities of advanced tree structures. Remember, these concepts are not just abstract theories, they are the building blocks of efficient and innovative software. By understanding how to choose the right data structure for a given task and how to implement efficient algorithms, you can unlock a world of possibilities in software development. So, keep experimenting, keep learning, and keep pushing the boundaries of what's possible with the power of data structures and algorithms.